Okay, now we've learned all about vector addition and scalar multiplication, but what if we wanted to multiply two vectors together? And before we actually learn what the dot product is, and you can see below that we're going to learn the dot product, I want you to think about the consequences of multiplying two vectors. Okay, so there might be two different outcomes you want. Okay, so let's think about two vectors. So the dot product, as you've been introduced to, actually just gives some relation between these two vectors defined by the magnitude of A. Let's define that A and magnitude of B. And we get some scalar result that is defined by that relationship. But there's actually another way to multiply vectors, which is called the cross product. This isn't accessible, by the way. The cross product actually returns a vector output from multiplication. Now this will be taught in uni first year for any STEM. If you want to research yourself, feel free to. If you actually want to Google it now, feel free to, but please watch the lecture. And if you actually have any questions about cross product, feel free to ask in the live chat as well. As long as the chat isn't too busy with genuine questions about the lecture content. Okay, I talked about the two different methods before. We're just gonna worry about dot product. Let's red circle it like it's a TikTok for little children. Dot product. And you've learned this in extension 1. So in extension 1, you would have seen B1, B2, that equals A1, B1 plus A2, B2. In extension 2, that extends to the third dimension. But honestly, nothing really actually changes. All that changes is that we add this extra component. I found it a lot easier to understand it in this way. If you're ever in a situation where you're proving things, you might actually want to use this, just sigma notation or sum notation. And if you actually just expand it out, this just actually becomes A1, B1 plus whatever the left-hand side was. Whatever feels comfortable for you in memorizing, do it, but I'm sure all of you will just think of it like this. Super easy, right? This times this plus this times this plus this times this. Super simplest way to remember it. All right, and we get this important result from dot product, that v dot v equals v squared. Let's prove it. One of my favorite things to do in maths is proving things. So when we prove things, for those of you who have done proofs, and it'll be important for you guys who haven't done proofs because we're going to be doing geometric proofs later. When we prove things, in general, we want to do arbitrary elements because this is called a direct proof. When students first learn proofs, they get stuck with trying to try every case, right? But here, v is going to be some vector in the third dimension. So if I wanted to test every single case, what would I have to do? Well, the cardinality of the size of set of the 3 dimensions is infinite because I can have infinite amount of results in the components. So what we have to do is actually declare an arbitrary element. So v1, v2, v3. If anyone wants to actually prove this themselves, feel free to just pause the video, pause the lecture, unmute it, and then go through with it, and then come back. So v1, v2, v3, and then let's figure out what the dot product of itself is. So v1 squared plus v2 squared plus v3 squared. Now if we recall the magnitude formula, this is v1 squared plus v2 squared plus v3 squared. If we square both sides, this becomes v1 squared plus v2 squared plus v3 squared. This is equation 2, equation 1. Equation 1 equals equation 2, therefore left hand side equals right hand side. So yeah, it's important to remember this. This will be also important in geometric proofs, and we'll come back to using this later on. Alright, find the dot product between 362 and negative 230. Okay, I like to personally just declare some vectors. A side note, cleanliness in solutions can win you marks. Now, when you're at school and you have terrible handwriting, that's fine, because you can literally go up to your marker or your teacher and ask them, what happened here? And then the marker will go, well, your handwriting was so bad I couldn't read it. And then you'll go, well, I meant this and this and that. And if your teacher's nice, they'll give you the marks. When it comes to the HSC, unfortunately, they're all external teachers who don't go to your school. So it's important from now forward to understand that you need to be clean in your solution. So that's why I actually declare these arbitrary vectors, because it's just cleaner. Okay, it's just cleaner and easier to understand. So even here, I'll go A, B equals 362 equals negative 230, which equals negative 6 plus 18 plus 0, which equals 12. Therefore, equals 12. Some of you may think this is a bit excessive. It might be, but it's always better to do more than do less. I know friends who lost a lot of marks due to having poor handwriting and poor mathematical working. So always make sure you're keeping your solutions clean. Even little things like keeping your equations in the same line is really important. Okay, as its name suggests, the dot product is written with a dot between two vectors. For example, A dot B, this is not the same as A times B, as this is the cross product, something very different. So this relates back to the convention and notation thing. If you write A times B for a dot product in your solution, if I'm your marker, I'm taking a mark off, because this is never the same as A dot B. Why? Because this produces a scalar and this produces a vector. So please, 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 please always use A dot B when you're talking about dot products. Okay. Like I said just that slide before, the result of the dot product is a scalar. If you're getting a vector, you're doing something wrong. Okay. Really ingrain this into your mind, because I have personally lost marks from doing this. Because while I did understand it was a scalar, I wrote this down in like a hurry in an exam, and then I lost a mark. I don't want any of you to do that, so just make sure you're doing it. Make sure you're not doing this. Yeah, always understand. It's good to understand with functions like the dot product, what is the input and what is the output. Okay, now a more formal definition. So the dot product can be defined if theta is the angle between two vectors A and B. So for two vectors A and B, and we have theta, then the dot product is defined as the magnitude of A times the magnitude of B times the cosine of the angle between A and B. excuse me. This is going to be really important later on. I think a big problem in extension 2 is that you're actually never really taught about what the dot product really means, but you need to understand it as some relationship that helps us explore more things about vectors. And it is related directly by a, b, cos theta here. Okay? And then we also get this important relationship that the angle between two vectors is defined by a dot b on the magnitude of a times the magnitude of b. Cool. Okay. Example question. Find the dot product of 2, 1, 4 and negative 1, 3, 2, and hence find the cosine of the angle between vectors. Okay. Let's see. All right. Again, keeping our solutions clean, let us define two vectors, a and b. Okay. A, b are in third dimension. And find the cosine of the angle. So always read the question. If you're reading this fast, you might just go, oh, find the angle between the vectors. Wrong. There goes a mark. Don't be silly. Always read the questions thoroughly. Okay. So let's refer back to our formal definition. A dot b equals the magnitude of a times the magnitude of b cos theta. Okay. So basically what they're asking us to do is to find cos theta, which equals a dot b on the magnitude of a times the magnitude of b. Okay. Okay, so let's find a dot b. Which equals negative 2 plus 3 plus 8, which equals 9. And the magnitude of a equals square root of 2 squared plus 1 squared plus 4 squared, which is equal to 4 plus 1 plus 16, which is root 21. And then b is equal to negative 1 squared plus 3 squared plus 2 squared, which is same as 1 plus 9 plus 4, which is root 14. Okay, so therefore cos theta will be 9 on root 7 times root 2 times root 7 times root 3. I'm just splitting up the surds so it's easy to simplify them. That becomes 9 on 7 root 6, and then you could rationalize it if you want to. In fact, you probably should, but I'm going to be skipping that step just for the sake of time. Okay. If you have any questions about this example we just solved, please leave it in the live chat and I'll be happy to respond. Okay, let's read this question. Let v tilde equals 1, 3, negative 1, and w tilde equals negative 2, negative 6, and beta. And they're two vectors in the third dimension. Find the value of beta so that the two vectors are perpendicular to each other. All right, let's fall back onto our formal definition. When are two lines perpendicular? When theta equals 90 degrees. Now, what happens when theta is 90 degrees? I'm going to give like 10 seconds for someone to answer in the live chat, even though I can't see it. And hopefully you guys figured out that cos 90 equals 0, and therefore the right hand side of this equation will always equal 0 when perpendicular. Yeah? Okay. So now we know the dot product of two vectors that are perpendicular to each other will always equal 0. So let's define this. When perpendicular, v w equals 0. Therefore, VW equals 1, 3, -1 times -2, -6 beta, which equals 0. So on the right hand side, that should equal 0. And let's expand the left hand side first. So left hand side, right hand side. Left hand side will become 1 times -2 plus 3 times -6 plus -1. Sorry, -1 times b, which equals 0. That's going to equal -2 minus 18 minus b equals 0. Equals -20 minus b equals 0. Minus b equals 20. And b equals -20. Sorry, I've been saying b, but it should be beta. So beta should equal -20. Just as a sanity check, let's go back and check if this is correct. So we've got 1, 3, -1, -2, -6, -20. This should equal 0. Let's just add the dividing line here. So that should equal -2 minus 18 plus 20 equals 0. -20 plus 20 equals 0. 0 equals 0. Yippee! Now we've solved it. And this relationship of two vectors being perpendicular is really, it's almost omnipresent in extension 2 proofs, because a lot of the time, when in maths, when we want to equate something equaling 0 is like, wow, this is what we really want. Like even when we solve quadratics, right? We want the right hand side to always equal 0. So this outcome is really important. So always make sure you're practicing questions like this and remembering this identity. Okay, another question. The vectors u equals a2 and v equals a minus 7 for a minus 1 are perpendicular. What are the possible values of a? If you want to try this question yourself, pause the lecture, read it, whatever, and come back. This is an extension 1 question actually from the 2022 question, exam, which I actually did. Oh, bad memories, maybe good memories. Okay, so when perpendicular, u dot v equals 0. The reason I like to just write definitions at the top of the page, it's not mandatory, you will get 4 marks without it, is that right now I'm doing a 2-hour lecture. Yeah. In the exam, in the extension 2 exam, you'll be doing a 3-hour exam. That's a really long time to be crunching numbers for. So personally, I find it really helpful to write definitions, make sure I'm being as verbose as possible in my explanations, because one, I might make a silly mistake in one of those 3 hours, in one of those moments, because I'm solving, upwards of 30, 40 questions, or at least parts of questions in those 3 hours. And I guarantee I'll get some silly mistake in this recording, right? So yeah, I personally, as an exam technique, I recommend writing definitions. So continuing on, u dot v equals a2 a minus 7 for a minus 1 a squared minus 7a plus 8a minus 2, which equals 8 squared plus a minus 2 equals 0. Let's recall to year 9 mathematics, resolving quadratics, 2, 1. We want this to be positive, so that becomes that. A plus 2, a minus 1 equals 0. So a equals -2, 1. Good thing about these vector questions is that we can sanity check. So let's sanity check. -9, -9. Just like by inspection, you can tell this is going to be true. 18 minus 18 equals 0. And for 1, -6, 7. Oh, what have I done wrong here? -6, 7. This becomes -6 plus 14. Oh, jeez. See what happens here, guys? You know, even I've gone through 3 extra math courses at university, which is far more extended than extension 2, and I still make silly mistakes. So please be careful. What I did before there was I did 4 times 2 because I just did that in the previous question. So it's going to be -6, 3. -6 plus 6 equals 0. Yep, so both of our solutions work. Awesome, so that works. This question will not be done. Okay, yep, we talked about this. If any of the vectors within the dot product, so if any of the 2 vectors in the dot product are 0, then the dot product is going to be 0. And if they are orthogonal or perpendicular, then it will also equal 0.